We have already understood complex numbers in the Cartesian form of expression, and during that time we discussed about finding the modulus and argument, right? So let's revisit that concept first. So I have a complex number z is equal to 2 minus 3i. Let's remind ourselves, we are now no longer in the real number domain, so no Cartesian plane. We are on the Argand diagram where we have a real axis and an imaginary axis. And 2 minus 3i means I have 2 units along the real axis, and minus 3i means I have 3 units on the negative side of the imaginary axis. So all the numbers on the imaginary axis have I connected to them, and that's what tells us that they are on the imaginary axis, and so the number is somewhere in the 4th quadrant. Correct? This is where the number is, and this is a sketch, of course not drawn to scale. This is called the Cartesian form of the number, where I have written it in the real number and the imaginary number form. I could also find 2 more details about z. One was called the modulus, and the way we defined modulus in our earlier video was what is the distance of the complex number from the origin. So how far is this number from the origin? And we used our knowledge of Pythagoras theorem to say that it is same like the distance formula, the real number square plus the imaginary part square. Now I'm not looking at minus 3, even if I put a minus, it's squaring, so it doesn't matter. I'm not going to take I into this because I am looking at the number of units on the imaginary axis, correct? So the square root of 4 plus 9 is 13. So it is square root of 13 units from the origin. That's the modulus. However, if I just tell you go square root of 13 units from the origin, you wouldn't know unless I tell you the direction. So that I needed one more aspect of z, and which was called the argument of z. This is how we write it in notations. And if I call this theta, then let me mark that I always measure the angles with respect to the positive real axis, same like how I used to do with the positive x-axis. Now I do it, and if I'm going clockwise, angles are negative. If I go anti-clockwise, angles are positive. So theta is, if I look carefully, my real number is 2 units and my imaginary part is minus 3 units, correct? And this forms a right angle triangle. So my knowledge of trigonometry says tan theta is opposite side upon adjacent side, so theta will be tan inverse. I'm assuming that you have been introduced to this part of trigonometry. If not, then you will be able to understand this once you learn trigonometry, and you can come back and look at this video at that time. So argument is tan inverse of minus 3 by 2, and negative angle tells me that it is going clockwise, which means it is in the 4th quadrant. So I could also express this number 2 minus 3i as root 13 at an angle of tan inverse of minus 3 by 2. So if the left hand side was called, and these both are equivalent expressions, this is called the Cartesian form of expression of a complex number, and the right hand side is the polar form of expression, where I write the modulus, which is usually denoted by r, and I write the argument, which is usually denoted by theta. So r angle theta is called the polar form of a complex number. In your calculator, there is an option for you to choose which form you want to use, because when you look at problems in complex numbers, you will realize each format has a use in a particular problem. Sometimes it is easier to operate in the Cartesian form and sometimes easier in the polar form. So again we come back to that analysis and approaches, right? that we must know more than one format. Okay, so if that is true, then let's look at one more problem and express it, but this time I'm giving you the complex number in a slightly different format. The complex number is now written as cos pi by 5 times cos pi by 3 plus I sin pi by 3. So what does this really mean? Okay, let me draw this diagram and show you what this would mean really. So 5 times cos pi by 3, 5 cos pi by 3 seems to be the real part, and 5 sin pi by 3 is the imaginary part. So this is the real part and this is the imaginary part. That's what is being given. Again, knowledge of trigonometry will be essential because you should be knowing the values of cos pi by 3. Pi by 3 is an angle expressed in the radian format, and pi by 3 in degrees would be 60 degrees. Cos 60 is half and sin 60 is root 3 by 2. So in the Cartesian format, this would have looked like this if I had written it in terms of numbers and not angles. So my complex number, by giving you in this format, what I have essentially given you is that 5 seems to be the magnitude because the cosine term will be along the real axis and the sine term will be perpendicular to the real axis. So 5 cos pi by 3 and 5 sin pi by 3, if those are the two real and imaginary parts, then modulus of the complex number is 5 and argument of this complex number is pi by 3. I don't even have to resolve it, and if you want, you may check what I have done. So what was the way you have to find the modulus? Real part square plus imaginary part square, correct? So modulus of z is square root of real part square plus imaginary part square, and I used my knowledge of trigonometry that cos square theta plus sin square theta is 1. And that's the reason, without resolving any further, I knew that the modulus is 5. And what about the argument? Well, I again knew that if argument of z is tan inverse of imaginary part upon real part, then sin theta upon cos theta is tan theta, and tan inverse of tan, that means a function followed by its inverse, will cancel each other and I will get the argument itself. In all these cases, you will need to have basic knowledge of trigonometry to understand how the polar form of argument and modulus is done. Modulus is simple because you know the distance formula, but for the polar form you will have to know the trigonometric rules, correct? Now, why is it useful sometimes? Now, it is useful because to do certain operations, the angles, it's easier to express them in the angle format. So let's do one last problem before we move. So the number z is 1 plus I. This is z1 number, and there's a z2 which is 1 minus I. And let's look at both the modulus and the argument. So the modulus will be square root of real part square plus imaginary part square. So modulus is 2, and the argument, this is z1, argument of z1 is tan inverse of 1 by 1. Tan inverse of 1 is 45 pi by 4 radians. And let's look at z2. So z2 will also have the same magnitude because the real part and the imaginary part in units is the same. I know the sign is different, but so the modulus is the same. However, the argument is this time tan inverse of -1, and which turns out to be minus pi by 4. Let's plot these points to see what is interesting about this. So on one side you may have noticed 1 plus I and 1 minus I are conjugates of themselves, right? This is how we define complex conjugate. What happens when conjugates are graphed on the argon diagram? So this is the real part and this is the imaginary part. Z1 is root 2 units from the origin at pi by 4 angle. This is Z1. And Z2 is, let me use a different color for it so you would see it clearly. Z2 is at the same unit but at minus pi by 4. So that's how complex conjugates look on the argon diagram. They will be reflections of each other in the real axis because only the imaginary part have opposite sign. The real part are the same and the units of the real and imaginary part are also the same. So that's what we know about the polar form. So let me summarize what we have learned. We have understood that the complex number can either be expressed in the Cartesian form or in the polar form, where the modulus becomes the R value and the argument becomes the theta value. So this number can also be expressed as R theta, which is called the polar form.